Hello everyone, I am Shivani and welcome to Civil Series. Today I am starting a new series of short notes of BMC Sub-Engineer and Junior Engineer exam. For the short notes, I choose a strength of material as a first subject. There are 12 subjects for the BMC exam, and from that 12 subject, strength of material is one of the important subject. And this is the syllabus for strength of material, and in the strength of material, stresses and strain is the very important points. Okay, from the stresses and strain, most of the questions are asked. And next part is principal stresses. Then movement is also included in mechanics. Okay, mechanics is base for strength of material, but in the BMC exam, BMC sub engineer exam, mechanics is not included. Okay, so mechanics is the base for strength of material, but mechanics is not included as a subject in a sub engineer exam. Then next part is deflection, shear forces, torsion theory, bending theory, beam, theories of buckling of columns. These are the points which are to be covered in a strength of material. Before discussing or before starting the strength of material, first we'll discuss what is the strength of material first. Okay. First, the strength of material comes from solid mechanics, and solid mechanics is a part of engineering science. Okay, engineering science is the biggest part. Under the engineering science, there are three parts, which is solid mechanics, fluid mechanics, and next is properties of material. For now, fluid mechanics and properties of materials, we not discuss about that here. We discuss about just the solid mechanics. Solid mechanics is divided into two parts. First is engineering mechanics and second is strength of material. First is engineering mechanics, second is strength of material. Engineering mechanics is related to rigid bodies. Okay, and strength of material is related to deformable bodies. So first of all, what is the rigid body? Okay, rigid body is that body in which the length before applying a load and length after applying a load and after removal of that applied load, the length before and length after is same in case of rigid bodies. And in case of deformable body, in case of deformable body, length before applying load and length after applying load, then after removal of that load, the length is not same in case of deformable bodies. In case of length, in case of depth, in case of width, the parameters are same. In case of depth and width, the parameters are same. Just we discuss all the properties in engineering mechanics related to rigid bodies. And in strength of material, we'll discuss the properties with respect to deformable bodies. This is the simple difference between engineering mechanics and strength of material. Okay, so from here we'll start the actual syllabus related to strength of material. In that, first is stress. Stress is nothing but an internal resisting force applied on a body. Internal resisting force is that force which is applied by any body for some particular application of force on other side. Okay, internal resisting force is a inner side of resisting force for any action. Per unit cross sectional area is nothing but a stress, and this stress is denoted by Newton per mm square, or the unit for the stress is Newton per mm square and megapascal. Then stress is divided into two types. First is normal stress and second is shear stress. Second is shear stress. Normal stress is nothing but, first point, internal resisting force in a normal stress is perpendicular to cross-sectional area, and in case of shear stress, the internal resisting force is parallel to cross-sectional area. Then second, normal stress is divided into two types: direct stress, direct normal stress and bending normal stress. Same in case of shear, it is divided into two types. First is direct shear stress and second is torsional shear stress. So this is the simplest explanation for the stress, and this part is also important. Most of the questions are asked from this part is the definition or the formula for the stress, and next is the unit. If they ask unit, then write it as a Newton per mm square, and if they ask in a Newton per meter square, then Newton per meter square is nothing but a Pascal, and if they want to change that Newton into dyne, then this is the conversion. 1 Newton is equals to 10 raised to 5 dyne. Okay, these kind of questions they ask from this part. Then second we move to strain. Then next is strain. Strain is nothing but a change in a dimension of any body. Change in a dimension of any body. Change in a dimension is possible when there is an application of some force on a body. Okay, change in a dimension to original dimension is nothing but a strain. And strain is a unitless quantity. Strain is unitless quantity. Strain is also a two types. First one is normal strain and second is shear strain. Second is shear strain. Normal strain is that strain in which change in dimension is possible. Change in dimension is possible, and in case of shear strain, change in shape is possible. Okay, so this is the simplest explanation for the strain, and here in case of a strain, most of the time they ask this formula, and sometimes they ask about the unit of strain. Then next is stress strain curve. Okay, in the stress strain curve, on the x-axis strain is there, and on the y-axis stress is there. Okay, remember that thing. If you draw any kind of graph, the independent quantity should be on a x-axis and dependent quantity is on a y-axis. Okay, stress is depend on strain, so that's why stress, we take stress on y-axis. Okay, so here this graph is related to mild steel. Okay, and for mild steel, after application of a force, first point we get, that point is limit of proportionality. Limit of proportionality, and that limit of proportionality is beyond which linear variation ceases. Means after the point A limit of proportionality, the stress is directly proportional to strain, does not remain constant. Okay, up to point A, stress is directly proportional to strain. Up to point A, stress is directly proportional to strain, and this is nothing but a Hooke's law. Okay, this is nothing but a Hooke's law. Then next, B point. B point is nothing but a elastic limit, and in that elastic limit, maximum stress in which original length is regained. Okay, up to that point, if we release the force applied on a material or force applied on a mild steel, if we release that force, then that material come to its original position. Okay, up to point B, that thing is happen. The next, C point, which is upper yield point. Okay, the next, C, first is C dash. C dash is upper yield point, then C is the lower yield point, and C is the lower yield point, which is actual yield point. From that C, the material does not regain its original position after removal of applied force. Okay, C is the fixed point from where the material completely goes to plastic state. Then next, C to D. C to D is the part nothing but a perfectly plastic region or a yield plateau region, and that CD in that plastic strain is equals to 10 to 15 times of elastic strain. Then next, from D to E. From D to E, that path is nothing but a strain hardening zone. In that strain hardening zone, the strain increases fast. That's why stress also increases fast. Then next point is E, and that E point is ultimate stress point. Ultimate stress point, in that stress correspond to ultimate stress. In that, this strain is 20% of mild steel. Mild steel, total mild steel strength is 100%, and up to the ultimate stress point, that strain is 20% here. This is the maximum point or maximum stress calculated on the mild steel, and that point is ultimate stress point. Then next, from E to F, that E to F is a necking region. In that necking region, the cross-sectional area of mild steel is drastically reduced. In that, the strain of that zone is nothing but a strain softening zone. D to E is strain hardening zone, and E to F is strain softening zone. Then last point is F. F is a fracture point. In that fracture point, stress about that point is a breaking stress, and strain about that point is a fracture strain. And strain is 25% of mild steel. Then one more point is important here. From starting of graph up to point B, there is an elastic region. After point B up to the point F, the region is plastic region. Then next, assumptions used in strength of material. First is the material is homogeneous and isotropic. Material is homogeneous and isotropic. So what is homogeneous and isotropic? Homogeneous is nothing but the same property in each and every point on a particular direction. Okay, consider this is in a body. Definition is same property in each and every point. Means this is 1 point, second, third, and fourth. These are the points on body. In each and every point, property is same, but in a particular direction. Means on this point in x direction, assume this as x direction, all the properties are same. Let's assume it as 1. Okay, and next, if here they said the property is same on each and every point but in a particular direction, means we consider this direction as a vertical, then the property for the vertical is same. Means for 2 the property is same. This is nothing but a homogeneous. Then in case of isotropic, the definition is same property in each and every direction at a particular point. Each and every direction means for every direction for x and y on a particular point the property is same. Means for this 1, then for this 2, then for this 3. This is nothing but the isotropic. Then second, Hooke's law is valid here. Hooke's law is valid. Hooke's law is nothing but stress is directly proportional to strain. Then next assumption is prismatic section is considered. Prismatic section considered, non-prismatic section not considered, or non-prismatic section is neglected. Prismatic section is that section in which the dimensions are same or equal throughout, and this is nothing but a non-prismatic section which has no dimensions. Then fourth is self-weight. Self-weight is neglected. Self-weight is neglected, but surface force is considered. Okay, so these are the 4 assumptions used in the strength of material. Then next is property of material. In that, first property is ductility. First property is ductility. Second is malleability. Malleability. So there is a one short trick for ductility and malleability. Remember dW for ductility and MS for malleability. dW means ductility causes wires and malleability causes sheets. Okay, so here W for wire, S for sheets. For making a wires, tension is required, and for making a sheets, compression is required. So this is just the ductility and malleability. Remember only these 2 points. Then next, brittleness. So brittleness is nothing but a lack of ductility. Lack of ductility. Then next property, toughness. So toughness is nothing but a resistance against fracture. Toughness is resistance against fracture. Then next is resilience. So what is resilience? Resilience is nothing but an ability to absorb the energy, ability to absorb energy up to its elastic limit, and release that energy after unloading. Resilience is the ability to absorb the energy within elastic limit and release that energy after unloading. Okay. Then resilience has one formula. Resilience is equals to sigma square divided by 2E into V. Okay. And then modulus of resilience. Modulus of resilience is resilience per unit volume. So for modulus of resilience, sigma square divided by 2E. This is the formula. Then next is proof resilience. Proof resilience. Proof resilience is nothing but a maximum value of resilience. Proof resilience is nothing but a maximum value of resilience. So this is the formula for the proof resilience. This is Y. The next is fatigue and endurance limit. 6 number. Fatigue and endurance limit. Fatigue is due to the repetitive loading. Fatigue is due to the repetitive loading, and endurance limit is that limit in which maximum value of stress up to which no fatigue cracks are developed is nothing but a endurance limit. Then last is creep. So creep is nothing but a permanent deformations due to continuous loading with a time. Permanent deformation due to continuous loading with time, or the continuous deformation with respect to time is nothing but a creep. So these are the properties of a material. First is ductility, second is malleability, then brittleness, toughness, resilience, fatigue and endurance limit, and last is creep. All are the important. Most of the time the questions are asked from grip, and next from fatigue, endurance limit, and sometimes they ask this DW and MS. The next is deflection of bar due to axial loading. There are two type of condition. First, load applied gradually, and second is load applied suddenly. Okay, if load applied gradually, then deflection is delta L is equals to PL by AE. And next, if load applied suddenly, then delta L is equals to twice of PL by AE. These are the simple formulas when load applied gradually and suddenly. But the important point in that case is AE is nothing but axial rigidity. Second, same thing as per the AE, the thing is EI, which is flexural rigidity. Then next, AE by L is axial stiffness. Same for EI by L. This is nothing but a flexural stiffness. Okay, so these are the important terms in this formula: AE, EI, AE by L and EI by L. Then next is deflection of bar due to axial loading. There are again two conditions here with a varying diameter. There are two type of bars. First is cylindrical bar and second one is rectangular bar. Second is rectangular bar. So this is the cylindrical shape. So this is the cylindrical shape. Here the delta L for the cylindrical bar is 4 PL divided by pi D1 D2 into E. E is the Young's modulus. The next for the rectangular bar, this is the rectangular bar. Then this is the formula for deflection of rectangular bar. Delta L is equals to PL divided by ET in bracket B1 minus B2 into log of B1 by B2. So these are the two formulas for the deflection of bar due to axial loading. These two formulas are directly asked into the exam. So these formulas are important. Then next is Poisson's ratio. Poisson's ratio is represented by mu or 1 by m. Poisson's ratio is nothing but mu is equals to lateral strain to longitudinal strain. Okay, so lateral strain is with respect to the depth and longitudinal strain is with respect to the linear dimension, means with respect to the length parameter. Lateral strain is nothing but the minus of delta D by D, and so here this is lateral, and the next is longitudinal. For longitudinal strain, delta L by L. Then next, these are the some values for the Poisson's ratio. Mu for cork is 0. For rubber is 0.5. For mild steel 0.3. For concrete 0.15 to 0.20. For cast iron 0.23 to 0.27. And the values of Poisson's ratio are between minus 1.5 to 0.5. Minus 1.5 is for the polymer sheet and 0.5 for the rubber. The next formulas related to different loadings. So first of all, one more important formula is their Hooke's law. You know, Hooke's law is nothing but stress directly proportional to strain. But stress directly proportional to strain, there is one constant between this. So stress is equals to, or stress by strain is equals to Young's modulus. Okay, Young's modulus, or also called as a modulus of elasticity. Modulus of elasticity, and this represented by E, capital E. So this is the Hooke's law, and we use this formula for the further formulas. So first condition is when we apply a force on a body in a one direction, like this. On this body, the force is applied on a one direction as a tension force, and these are the formulas for the strain in x direction and strain in y direction. The next case, if the loading is applied on a two sides in x and y direction, then if force applied on a two side, then these are the formulas of strain about x-axis and strain about y-axis. Then third condition, if force is applied on a three sides, means x, y and z. So in all three directions the forces are applied, then this is the formulas for the strains applied in the x direction, applied in the y direction and z direction. So these are the three formulas. So remember, first condition, the forces applied only in a x direction. then this is the formula. Then in second, forces applied on both direction in x and y, and in third case, forces applied on a three directions x, y and z. Then these are the formulas for the strains with different loading conditions. Then next is volumetric strain. So volumetric strain is nothing but a ratio of change in a volume to original volume. So this is the formula for volumetric strain, and this is also a unitless quantity. Then next there are two formulas of volumetric strain in cylinder and volumetric strain in sphere. So these are the two formulas for cylinder and sphere for the volumetric strain. Elastic constant. There are different elastic constants for different material. So for homogeneous and isotropic material, elastic constants are 4 and 2. Here 2 are independent. Then second, for orthotropic material, elastic constants are 9 and 12. Here 12 are independent. Then next, anisotropic material. Elastic constants are 21 and infinite. Here 21 is independent. Okay. Then again, elastic constant is related to Hooke's law. There is one elastic constant which is Young's modulus or modulus of rigidity. But we discussed it earlier, so we are not discussing this here again. The next is bulk modulus. Bulk modulus is represented by K. Bulk modulus is nothing but a normal stress to volumetric strain. Normal stress to volumetric strain, sigma by epsilon V. Then next is shear modulus. Shear modulus is also called as modulus of rigidity. Modulus of rigidity represented by G. And shear modulus is nothing but a shear stress to shear strain, tau by phi. This is nothing but a shear modulus. Then next, these are the different formulas which is related to the Young's modulus or shear modulus, then bulk modulus and Poisson's ratio. By using all the four elastic constant, there are few formulas and which are very important. So first is E is equals to 2G 1 plus mu. Okay, here we calculate Young's modulus, shear modulus and Poisson's ratio. This is the first formula. Then second formula is E is equals to 3K in bracket 1 minus 2 mu. This is second formula. Then third formula I write here. So third formula is E is equals to 9 kg divided by 3K plus G. 9 kg divided by 3K plus G. Then last fourth formula is mu is equals to 3K minus 2G divided by 2G plus 6K. All the four formulas are important here. So you can write that formulas. So we can remove this for writing. You write that formulas. All the four formulas are important here. So write this and remember all the four formulas. And this bulk modulus and okay. So this is the important. So remember all this. The next point is then next is temperature stresses. Due to temperature, many changes are happening into the construction materials. If temperature is increased, then the material get enlarged by some dimension, and if the temperature get decreased by the regular temperature, then that material get reduced in a size. Okay, these are the simple effects due to the temperature stresses. Here first we discuss the formula related to temperature stress, and then second temperature strain. So for temperature stress, the formula is L alpha into delta T, and for strain alpha into delta T. Here alpha is nothing but a coefficient of thermal expansion. Coefficient of thermal expansion. Okay, and there are different values of thermal expansions. For mild steel and for concrete, the values of coefficient of thermal expansions are same, 12 into 10 raised to minus 6 per degree Celsius. For concrete, there is a range, 6 into 10 raised to minus 6 to 12 into 10 raised to minus 6 per degree Celsius. For copper, 16 into 10 raised to minus 6. For brass, 19 into 10 raised to minus 6. For aluminium, 23 into 10 raised to minus 6. So these are the values of coefficient of thermal expansion. So here I completed a few points, and next points we'll see in a next video. So till then, watch this video and practice it.